Now I would like to introduce another speaker, a very good speaker. It's myself. So my name is Martin Macas. I'm working here as a researcher at CIIRC. I'm part of two research groups. First is focusing on intelligent systems for production and for industry. And I'm also interested in healthcare and biomedical engineering, and I'm involved in cognitive system research group. Okay, so my task is to describe what we did, what we are doing last 3 years with Škoda Auto. We had project which is focused on it. The project under which this is solved is called National Competence Center Cybernetics and Artificial Intelligence. It finished last year, and actually 2 days ago I finished the final report for that, and we made it in team. So I will describe the team of CIIRC. It's me, Petr Kadera, the head of Intelligent Systems Group, and also some students and other colleagues. And there was also a team from Škoda Auto, which are people from quality control department of Škoda. And we got some nice results, which I would like to show you here. The whole project was focused mainly on one particular product and one particular operation of production, the machining of engine head. I'm sorry for this picture. This is not the engine head which we focus, but I love this. I like the sensor here. I'm sorry. Oh, okay, the sensor here. So that's why I put it here. There's actually there are many different types of engine heads produced in Škoda, machined. And their quality is somehow checked, inspected, and controlled. The project was focused on improving or making more efficient the process of quality control and quality assurance, let's say. This is actually the current control loop which we use, and the machining process is situated here. This is the production process, but we can be very general. It can be any production process, and it can be even, for example, healthcare process in hospitals, some medication or control of diabetic patient or something else. So this is production process here, the machining of engine head. It produces the parts. And the input of this process is the part from previous operation. So this whole is actually part of multiple machining operations performed on multiple different machines. And we focused only on one particular operation. So I can ignore this part here, and we can assure that we have a good quality part coming into the production process, the production operation. This is the machine, and are the parts, the engine heads that are machined and on which actually holes and surfaces are produced. Then from time to time, according to some sampling plan, it's called kontrolní plán operace, control plan of operation. From time to time, one part is taken and some quality characteristics are measured on it. As you can see here, this is the coordinate measuring system, and produces some quality characteristics, like, for example, diameters of holes, of positions, and so on, etc., etc. And based on those measurements, there is some system which tries to detect if the process is okay or not, if the process is in control or out of control. If there is some problem detected here, the operator tries to diagnose the whole process, tries to find out where the problem is, and remove it by selecting a proper corrective or control action. So it's actually a control loop, this one. And in this way, the process is kept in control, which means is producing good quality parts. This is an example what actually is measured in that part measurement here in this box. This is one quality characteristic, and this here is time or sampled parts. There are also defined some control limits or tolerance limits at this moment or in past, and also now partly. Those limits are computed from a specification on or tolerance limits. So they are not computed somehow from data, but the construction department or some designers give some information about tolerance limits that should not be exceeded to keep the good quality of the product. And those control limits are just, for example, 80% of those tolerance limits. So it's not computed from the data. Data are not used, and also only some other algorithms are used by designers. So if the measured value of quality characteristic is out of those limits, then the operator tries to correct the problem, find out the problem and correct it. You can see an example of quality characteristic on this picture, which is diameter of some hole, and you can see that there are many different holes and many different surfaces, which is very important and relevant. We got some data. Unfortunately, at the beginning, we absolutely ignored what our colleagues from Liberec told you before, and we just got some Excel data that we got from Škoda. And we also ignored some internal processes of Škoda at the beginning. Then the IT department told us, okay, it's not correct, and you have to be you have to follow our internal rules. We in Škoda, in this department, they are using Histat software, which is statistical software, which just checks the limits and the values of quality characteristics. It warns the operator that something happens, and so on and so on. And currently we are initiating a collaboration with this company which is producing Histat. It's called Deribet company from Czech Republic, from Beroun, by the way. And in our future effort, we would like to collaborate closely with them, and they want to collaborate obviously with us. Okay, this is another example of what we can measure. This is just one quality characteristic. Here you can see the nominal value, measured values in time. You can see the tolerance limits, and also 80% control limits. So if those limits, those control limits are exceeded, then the operator reacts somehow. This is another example. You can see that all those measured values are very far away from the nominal, from the boundaries, from the control limits. This means that this quality characteristic never exceeded the limits, and probably it will never exceed them in future. So it means that maybe we don't need to measure it so often. And this is very important, because currently, actually, here we are, or they are measuring 700 of such quality characteristics. So you can imagine that they have like 700 of such detectors based on this picture, a so-called control chart. And they are checking 700 times the value of each characteristic, and this probably is time consuming first. The measurement is time consuming, because the measurement of one engine head takes about 45 minutes. And if we have multiple machines, multiple fixtures, we have multiple different types of engine head, it means, or it implies, that only one engine head of one type from one machine is measured per day. or something like that. This, you can imagine, is not so efficient if you consider that or take into account that there is like hundreds, 300-400 of parts produced per day. So it's one part is sampled and controlled per day. So this could be somehow improved. For example, this quality characteristic does not need to be measured, maybe, but we don't know. And this means that we could select and change the control plan of operation. Another problem is that if we have one characteristic, it's okay, it is okay. If we have multiple quality characteristics, it can be a problem. Here you can see two, and this is a scatter plot which describes the data in 2D. And for example, you can see this point here, which is definitely an anomaly. It's something different from the other points, and it can represent a problem. But if we take into account those control limits individually for each of those control charts, then we get some boundary here, but this point is inside the boundary. This is common problem, which is well known, and it can, okay, maybe this is not so important, and this is common problem, sorry. And second problem which we can have is that if we measure one individual quality characteristic and try to detect it, then the detector, this control chart, has some probability of false alarm or false positive observation and or decision. And in that case, you can imagine that if you measure 700 times something and you test it, then the probability that at least one of those values, of those quality characteristic values, is accidentally out of boundaries increases rapidly. I will not describe those probabilistic or those equations, but believe me, it increases rapidly. And for like 700 quality characteristics, for example, it can increase to 80%. And we found that the ratio of parts that had at least one quality characteristic out of boundaries was 70%. So 70% in our case, 70% of parts are detected as being somehow abnormal, which is incorrect. Obviously, the operators use their expert knowledge and ignore it, or they know what happens, so they say, okay, this is because I have this new drill, for example, and it's typically wider, so it will improve in time, and I will ignore it at this moment, and so on. So, but it can be a problem, because very often the operator can ignore also a real problem in such a case. Okay, so here is the same example as I shown you before. This is just a toy problem here. And this is the same scatter plot, so once more. And solution of this problem are multivariate systems, multivariate techniques. Here is one of them, which is elliptical boundary, which can be produced by a so-called Hotelink T-square diagram, which is also part of some statistical softwares, and like commercial statistical softwares for statistical process control. And it's multivariate technique, which can be very useful, however, only if there are some assumptions met. For example, this technique actually assumes that you have normally distributed data, which is, however, very often not correct, not true. And in that case, those techniques can lead to erroneous response. Okay, I will skip this because of time. This is an example of that Hotelink technique on the real data. Here you can see 3 quality characteristics, and here you can see a score, which says how abnormal the particular parts that were measured are. So you can see some points here that are below then threshold, and in that case, the score of abnormality is too high, and you can say, okay, it's abnormal. In our use case, we had many problems. First of all, we had too high number of variables, 700 variables. Second, some of those variables are strongly correlated, which is an important problem if you are using that method that I shown you before, the current method, where you have just rectangular boundary. Third, there is very often normality violated, and very often autocorrelation is present, and there are many other problems. And those imply that common techniques that are using somehow data and are learning the boundaries, the control boundaries from the data, cannot be used. And in such a case, what I want to point out here is that we can use the machine learning. We applied classification methods and anomaly detection methods, and especially for anomaly detection, you can imagine that we want to somehow create an envelope of the data that we measure data that are from the in-control process, and we try to create envelope which efficiently covers the normal data. And then if something is out of this boundary, this envelope, we can say it is anomaly. We used so-called one-class classification methods, support vector machines. It's not so important, and tried to, at the beginning, to improve this part, this post-process non-OK state detection or out-of-control state detection. It looked very nice, and we got some results. Method was able to learn good boundaries, and we made many different types of testing, and it worked very, very well. Here you can see an example of the boundaries. It's still the same picture, but for real data. You can see how different shapes of the data in different, for different couples, pairs of variables, how they can be efficiently modeled by this green boundary, which is the support vector machine. And maybe, and this is another example, sorry for this, it's slightly interactive. So here you can see, just for 2D, you can see the normal Shewhart control chart, which is something which I described at the beginning. This is the Hoche link, which assumes the normal distribution of the data, and this is the support vector machine method. And those points that are real anomalies, that we knew that those are anomalies or problematic states, are separated by this blue boundary. We created an application. Currently, we are using it just for developmental purposes, and we expect that those methods will be implemented into as modules for the Diribet company's Histat system. A very important thing is that what I shown you before, the operator will not use it because they will say, okay, it tells me there is some problem, but I don't believe it. I don't know why it thinks so. So a very important problem was to detect which quality characteristics were somehow suspicious. What was the problem? Because they are used to it. They are using it. They are actually, they have system which tells them, okay, this quality characteristic exceeded the boundary, the limits, upper control limits. And here, this is missing. So a big problem of those methods which we solved was to identify why the classifier, why the AI thinks that some part is suspicious and there is some problem. Yeah. This is a very important problem of many AI methods, and I will now maybe skip this, and I will describe something more about this interpretation. It's called interpretation, and what we want to do is to find a system which says a potential problem was detected because, for example, diameter of hole 1 and diameter of hole 2 have some suspicious, maybe too high values, for example. And this is exactly what the operator expects. It's not so simple task. It's quite ambiguous, and it's not so easily solvable. I will maybe, because I don't have so much time now, probably. I have just 5 minutes. Is it correct? Okay. But we try to use many methods. I will skip those and I will show this description. Finally, we use this method, which is called local interpretable modal agnostic explanation, LIME, abbreviated as LIME. And this is an example. This is an example of classification problem, classification image. And this is the original picture. And the neural network here tries to predict why the system thinks why the system tries to say why the neural network thinks that there is, for example, a guitar, electric guitar. This is the part of the picture which supports the hypothesis of neural network that there is electric guitar. This is the part, those are the parts of pictures that support hypothesis that there is normal guitar, and this is the part that support hypothesis that there is the dog. And this is exactly what we solved, because those pixels are inputs of AI, of machine learning method or predictor, and we want to know which inputs are responsible for positive detection of out of control state. So we applied this method and implemented it as well. This is where explainable AI starts, actually. Okay, we made many different tests and so on. And now we are getting from this part to the diagnosis, because what the interpretation is very close to diagnosis. And but now, instead of saying only which inputs are responsible for positive detection, we try to find out what was the reason of positive detection. Where is the problem in the process, which is much more complicated. And I'm very happy that we have our colleague Vašek Jirkovský here, who is focusing on ontologies and semantic web technologies and so on, because this is why we tried to implement, or we found out that for many reasons, not only this, we need something which is a formal representation of the process, of the knowledge about the structure of the process and so on. Because we had many data sets, different data sets, we had many discussions and many people that knew what is the structure of the process, but we never had the whole view on the whole process of measurement and process of production. That's why we tried to create an ontology. Here you can see just a small example of the concept. It's quite old image, now it looks absolutely differently. Those are some individuals of ontology. And there are many different types of applications of such ontology and some formal representation. First, the diagnostical purposes, because we can find out, for example, if one quality characteristic is suspicious, we can find out which tool influences this quality characteristic, or which coordinate system setting, like called 0 point, which of those is influencing this this quality characteristic, and so on and so on. Second, it can help us to simulate the whole process numerically, and we use the numerical simulation very often for evaluation and validation of that detectors that I shown you before. And last but not least, understanding measurement structure of measurement plan optimization. We are trying to move on and instead only improving the detection of problem, we are trying to improve the whole measurement plan. As I showed you, some things need not to be measured so often. Some of those are very critical and should be measured often. So we defined another task to optimize the sampling plan, which you saw before. The task is actually to to find such subset of measured quality characteristics which minimizes some criterion function, which is the quality cost. And we are trying to estimate the quality cost. And to do it, we need to know the whole structure, because there are some elements like circles and surfaces. And from those elements, we are computing the quality characteristics themselves, like diameters and so on. And this complicated structure must be used by mathematical formulation of quality cost, but I don't have time to describe it in details now. Okay, we solved many other problems, like for example, at the beginning, we had the data in which one quality characteristic was hidden under 12 different names, and it was just one quality characteristic. If you run AI, which is using such data, obviously you cannot get a good output. So that's why we had many smaller technical problems that were solved,